Okay, so I think we have to call him doctor now. And he was a student of Gustavo Burman at USP, who's going to perimeter as a postdoc. And he's going to talk about baryogenesis just around the corner, generating the matter symmetry near the weak scale.
Okay, thank you, Roger. Thank you for the invitation. It's really nice to be here. This very first place. No, not first time in this room, but not first time.
Well, then you should come also when you don't talk.
Exactly.
Of course. Yeah, this is a good reminder that I should. So today I'm going to talk about baryogenesis at lower scales than usually thought of baryogenesis. And I will try to motivate it. So this is like the rough outline of my talk. First, I will just comment on some motivations on the matter and antimatter asymmetry. Then we go through two examples of these lower scales baryogenesis models. This first one is generally called low temperature baryogenesis. Is related to long-lived particles. And the second one is more known electric baryogenesis and the electric phase transition. I want to comment a little bit on like how the status of the calculations in some like quantum field theory context. And then I'll summarize and give some final thoughts. So we know that since the universe expands, it was much smaller in the past, and since it was smaller, it also means it was hotter. And this is a very good opportunity for particle physics because then we can access the standard model and maybe new degrees of freedom that we don't know yet once you go to the past. So if we rewind here cosmic time, we go from today to some very well-known epochs of the universe like the CMB, BBN. But before BBN, not much is known. We know some things, like, for example, we know that there is an asymmetry that should have been generated before. We know that there must be something like inflation because we have like these problems of causality when we look at the sky. So we know a bunch of things that should happen here. We don't know in which scale and why or how. But
These are not in energy order. They are breaking.
It's the inverse order.
Yeah,
It's the inverse.
The inverse.
That way. It's going to the
Ah,
back.
they, sorry.
Yes,
I also had the same problem.
That's why I was.
I usually think of going that way.
I had to do, because I wanted to do it like this, I had to do this figure myself because there is no in the online. So time is going this way, temperature is going this way. Okay. So one of these things that I commented we know that must have happened before BBN, for example, is related to this puzzle of matter and antimatter. So we know that the universe is composed of matter, and we can ask ourselves if there is antimatter around, and only in particle accelerators because we can produce them, and in cosmic rays. But in cosmic rays, you can calculate the number of antiprotons divided by the number of protons you see, and this is 10 to the minus 4. This is consistent with the secondary emission of antiprotons, so just like particle physics processes as they propagate. So this is not like some primordial antimatter asymmetry. And even more strongly, there is evidence from BBN and CMB against any primary form of antimatter in the universe. So it really looks like we are dominated of matter, and this has been like that for a very long time. So this evidence, so here I call this parameter eta is basically the number of matter baryons minus the number of antibaryons normalized by something. So here I can choose to be the number density of photons, and we find this number 10 to the minus 10, which is small but very hard to explain, as I will comment. And if you assume that there was some asymmetry, you get like a very good fit for example, the origin of light nuclei. So here in this plot is the results of BBN, Big Bang nucleosynthesis, and here I show the prediction. These lines here are the predictions of the standard model for different types of elements like helium-4, deuterium, helium-3, and lithium, all normalized. So these are normalized by the hydrogen, and we can put here the predictions. So here these square boxes are the observations, and here is the band that CMB, for example, BBN predicts you should live. So if you fit our model, you can see that there's very good agreement with helium, deuterium, and helium. There's a little bit problem with lithium. This is a famous problem, but overall you get a good picture.
Does it still hold?
It still holds. And people still think about it today. I guess if you ask different people, they have different opinions. But the consensus is more like maybe it's astrophysics, the reason for this discrepancy. I don't know a lot about it. But
This box with the dots.
so this is like some true sigma and then some other, I don't remember, but some other,
3C.
yeah, maybe something like that.
So let me see if I understood. So the symmetry is already understood.
The symmetry is there. We have evidence for it from BBM because we fit I'll comment a little bit more on that. But if you fit what we expect from the standard model calculations, we get these lines here. And then if you use data, for example, these boxes, you can pinpoint where the asymmetry must be. So around here, which is this value. Good. And if you go to CMB, CMB is very sensitive to, for example, the baryon energy density. If you change it a little bit, then you would change and mess up with this really beautiful picture of the lambda CDM. So to get a deeper understanding of that, we can imagine that we started out in equilibrium. So NB was equal to the number of baryons the number of baryons was equal to the number of antibaryons. These boxes should contain the same number. And if you assume they are in equilibrium, you have this distribution. Here's the usual Boltzmann factor of this species. So N is the nucleon, but these are for baryons. Now we can compute the freeze-out temperature in which these interactions stop. So they start to annihilate, and at some point this stops. This happens when the expansion of the universe is equal to the rate of these interactions. And if you equal them, you can solve for the temperature freeze-out. The cross-section of this process is roughly the pion mass, 1 over the pion mass squared. So if you solve for that, you find a freeze-out temperature of 20 MeV, more or less. So you can put this 20 MeV here in this expression to see how much baryons you are left with. And you find out that this is 10 to the minus 8, which is 8 orders of magnitude below the value we observe from there. So these guys will annihilate themselves, and you are left with almost nothing. So very hard to explain. And if you had some primordial asymmetry, so here I'm considering 30 billion and 1 numbers of protons, of baryons, and 30 billion without the 1, 30 billion.
Did you count them?
No, and probably this is not correct, but representative. And then if they annihilate, you end up with this one left. So it looks like this is a small asymmetry. It looks like this might not be so hard to achieve, but that's not true. It's not very easy to generate this very small asymmetry in the universe. So 58 years ago, Sakharov formulated 3 conditions to fulfill baryogenesis. Baryogenesis is this process in which you generate asymmetry.
The H is after the K.
Oh, yes, I was careful to write it. Okay, I made a mistake. Ages before, yeah, swapped. So the 3 conditions are: first, you need the violation of baryon number, because some of the baryons we see, they conserve some symmetry of the standard model, which is baryon number. Second, you need C and CP violation. These are related to how particles transform to antiparticles. And you also need out of equilibrium processes, because if you had equilibrium, the number densities should be the same of baryons and antibaryons. So you must have something that will drive them to be different. And I think it's very impressive that Sakharov could find this even before the standard model, or even before they found like asymptotic freedom. Asymptotic freedom is a realization that QCD becomes perturbative at higher energies. So before that, people didn't know how to do calculations in the universe. So I don't know how could he be thinking about the very early universe without having a theory for it, but he could, and this is why he's very famous, I guess.
You won the Nobel Prize.
Oh, did he? Okay.
For peace.
What?
For peace. You don't know?
I didn't know. I should put this in the slides.
For P. Okay.
Okay, so you have these conditions. Famously, the standard model, the theory we know of particle physics, cannot explain the baryon symmetry, but it had potential because if you look at baryon number violation, at first, if you look at the Lagrangian, you wouldn't say that it's violated, but there are some configurations. So this is non-perturbative configuration called spectrum, which can violate a combination of baryon number and lepton number. And you could think of a way of using that to do baryogenesis. You do have CP violation. This comes from the weak interactions. And you, in principle, could have some out of equilibrium processes because there is an electric phase transition. So the Higgs was in the early universe, it was in the unbroken phase, and then it transitioned to the broken phase. So maybe that could lead to some out of equilibrium processes. But these ingredients in the standard model do not mix well. They are like vinegar and milk because the electric phase transition is second order. And we are pretty sure that was confirmed by Laris. So there is no, so what is a first order phase transition? I'll comment a little bit more, but well, first order phase transition is a transition in which the minimum are separated by a barrier, and then you can generate some bubbles in the early universe. These bubbles mean that the universe was out of equilibrium because it wasn't homogeneous at the time, right? So you could have some of these out of equilibrium processes, but the standard model doesn't have that, and CP violation is small. So you can quantify what is maximal CP violation in the standard model. It's proportional to the differences of the quark masses, and because of that combination, it's smaller than we would need to get to the tangent minus 10. So we need to go to physics beyond the standard model, and we usually have a traditional physics beyond the standard model scenario, which, for example, it was a convergence of several ideas in the 80s, 90s. So, for example, in the TeV, a very well-motivated model is supersymmetry, so this MSSM. This predicted dark matter, so like things kind of fitted together. And then if you can do this physics at the TeV, you can start to think about physics at very, very high energies. So this is what people usually did. Here, these high energies, I will comment on that too, but baryogenesis model naturally lives there. They are very well motivated by, for example, they can have some connection with the seesaw, which explains the neutrino masses. But this also means that if you have baryogenesis there in that range, this is very hard to test. So kind of a tricky position we are. But we are free to think of models of baryogenesis at small scales. It's a little bit harder. And mostly, since we haven't found any new physics yet at the TeV, I think things are up in the air, so we can start having like thinking different ideas, or maybe going to look for new signals of baryogenesis. And this is a program that has been gaining a little bit of momentum after like the LHC or something like that.
You can also use EFT, for instance, and have dimension 6 operators with the standard model of fields and have successful baryogenesis.
But you mean at high energies, right?
Dimension 6 operators.
Yes, so we have to be careful with dimension 6 because it's really easy to generate proton decay. So the reason why baryogenesis models naturally
Dimension 6 in the Higgs sector. So
in the Higgs sector,
yeah.
I see.
So H bar H.
And then they do something like electric. Okay, yes, that's
I think Christophe Bourgian has papers on that.
So he's exploring this idea that you could have a first order phase transition.
Yeah, first order phase with extra high dimensional pressure.
Yeah, so I think this one would classify it like electric baryogenesis model. So there are several testable baryogenesis models. People have proposed that. One is this one that I will talk first, low temperature baryogenesis, but you can also do electric, in which you explore. It's okay. You can have electric baryogenesis, which is inspired by these first order phase transitions. You could have other things like asymmetric dark matter models, in which dark matter is also asymmetric, and the asymmetry is generated together. Mesogenesis is a fun idea which you use the CP violation of mesons, and you can also do resonant leptogenesis, for example, in which you can enhance the CP symmetry of usual leptogens. So let me start with this one, low temperature baryogenesis. This is connected to long-lived particles. This is related to these two papers I did with Gustavo. So let's go back a little bit, and baryon number is defined as a global symmetry of the standard model. It's basically a rotation you can do in all baryon fields. Lepton number is a similar thing. You can rotate independently the electron, mu, and tau leptons of the standard model. But baryon number is a really, really good symmetry of the standard model. And we say that because you can measure things like proton decay, and it's a really, really strong bound. So you see here it's 2.4, 34 years. You can also measure it, different channels. You can also measure things like neutral oscillations through anti-neutrons. This constrains these processes that violate baryon number, which you need to do baryogenesis. So if you think of like some EFT, so just some operator here that violates baryon number, you have to put some scale here because this is a dimension 6 operator, so the b to the square. And you impose this bound, you get that the scale should be 10 to the 16 GeV. So really high. So proton decay and these processes, they seem to impose these strong bounds, but it's possible to do baryon number violation without proton decay. I will show you how, but to be able to do these models that violate baryon number at low scales, you need that, right? You cannot violate proton.
What's the bound for the neutron and neutron selection? What's the bound? What's the dimension? Has to be regular. I forgot the dimension.
Sorry, what do you
No,
mean?
what's the bound on the scale from this?
What scale does imply? I see. I have to think of an operator that violates that generates neutron oscillation.
Is the dimension?
Yes. If you build like UDD,
Yeah.
this is dimension 3, 6, 8, 9.
Right.
But I don't know.
Probably the scale is very low.
Yeah, but it's not so low. So if you have to be careful. Neutron oscillation bounds is usually the first thing if you don't have proton decay, is the next thing that I would be careful. And the bounds will improve in a little bit because they're doing new experiments. But you have to be careful. Okay, so
Well, the TV is safe, I guess. That way.
not so much. You
No,
have to,
not even.
yes, sometimes you can go like 10 meters. If you have some, for example, if you have some QCD charge in your scalar, and it induces oscillations, depending. Oh, of course, yes, depends on the model, I should say.
So it could be around the corner.
It could be around, yeah. So I do the simplest idea. It's just you have a new particle that decays to baryons, right? Doesn't do anything else. And it generates asymmetry when it's decaying. So to do that, these new states must be semi-invisible because if you had color or electric charge, this would be really easy to see at the LHC. And you also need to fulfill the out of equilibrium condition. So the rate of this decay is smaller than Hubble, or the rate of interactions of this particle to be smaller than Hubble, so that this is out of equilibrium, is not in the thermal plasma. And if you translate this condition through a lifetime, which is inverse of this rate, and you multiply by C, you get a decay length that is macroscopic. So for example, if you take a mass of this M, this particle that decays to be 100 GeV, this decay length can be 20 millimeters, for example. And that's macroscopic, and that's if you produce this at the LHC, it would be a displaced vertex. And so it will be produced at the interaction point and will decay inside the detector, but not exactly at the center. So you could try to comment a little bit more. But our condition is that baryogenesis should happen before BBN. So I'll present a model in which you have 3 Majorana fermions, this N1, 2, 3, and you need a scalar 2. I would just use like this out of equilibrium decays of N to U, DD. This combination has to be neutral. So you really have to use up type quark, down type quark, down type quark. Not necessarily the up and down, could be like the the charm and the strain, for example, or the charm at the bottom. So you can build an effective Lagrangian that would look like this. So it's n here, UDD, and you can have some flavor indices, and you divide by this mx squared because it's a dimension 6 operator. And I also need this complex scalar, so I will write the simplest thing, which is a Yukawa coupling between these n's and the
Can this also contribute to neutrino masses?
Yes, this is a very important point. In this model, no. In this model, you have to justify why this doesn't mix with the neutrinos through the Higgs portal. Oops. Otherwise, you generate proton decay. Oh, yes. If you can do this. Is this fine? Let me see. Okay.
Why is this called out of equilibrium decay?
Because it. So maybe you can go to this slide now. Then it will be clear. So here's a timeline of events. First, these I will call N2. I will justify why I'm choosing 2 to be the guy that decays to generate the asymmetry. But first, this N2 is in equilibrium with the standard model plasma. Since it has its interactions with the quarks, it will be following the thermal distribution. So it will have some abundance of them. But at some point here in this model, like be around, for some parameters will be around 300 GeV, and N2 freezes out of the plasma. So it stops interacting and it's not thermally produced through the standard model anymore, and its abundance is fixed throughout the evolution of the universe. At some point, you reach the mass of N2, and here choose 150 GeV, and this N2 becomes non-relativistic, and later on, it will decay. So this is what it means, because I have a very long-lived guy that is produced in the thermal plasma, freezes out, and only after that it will decay. Okay. And this decay is satisfies the Sakharov's conditions and can generate the asymmetry. So you see here is 10 GeV. This is what I'm calling low temperature. So to calculate that parameter, 10 to the minus 10, I was talking in the beginning, I will calculate this baryon symmetry. Here I'm using Y. It's because it's normalized to the entropy, but it's basically the same thing as that eta I was showing. And this will be a product of different things. So the yield, CP asymmetry, and the branching ratio, I'll explain them one by one. So first thing you produce this N in the thermal path. So you have some abundance of it, right? So I call it the yield, which is the number density of this N2, and you divide by entropy. And for small N2 couplings, this will decouple early. So here I said like 300 GeV. So if you choose this X scale to be 2 TeV, for example, this is the effective scale of the operator. This freezes out early, and it decouples to the plasma relativistically, so you can use the relativistic distribution for this N. So we just have this thing, depending on the number of degrees of freedom.
What's kappa 2 again?
Kappa 2 is the coupling. Here, I should have emphasized. So I have these couplings, and they control how much was coupled to the path, and they control also the decay.
And C controls the mass.
C, no, this doesn't get a PEV. So
Phi doesn't get it.
no, it's just a scalar living there. In another project, I do break the symmetry, but Phi doesn't get a mass.
But N has a mass, right?
N has a mass. Yeah, I'm not
Where
right.
mass comes from.
It's just a Majorana mass. So I don't know.
Not Dirac.
Not a Dirac. Yes, that's very good. Okay, so now you produce these ends, and they have to decay more to particles than antiparticles. So to measure that, I have this CP symmetry parameter. This is the rate of the case of N2 to UDD minus the rate of the case of N2 to anti-UDDs. And you normalize by the sum. And if you calculate that, I won't show here, but this this is proportional to the imaginary part of the interference between the tree-level decay, which is this one, and the one-loop contribution. So this is very important, this one-loop contribution, because this is what allows you to decay more to particles than antiparticles. And the product of these things would have an imaginary part. So the couplings, they are generally complex. And this CP asymmetry will be proportional to some relative phase between these couplings, which, since they are not related to each other, this should be like some order 1 number. And you divide by this K2 squared because you have the sum here. So these are the couplings that enter these diagrams. K2 enters this one, K3 enters in this vertex, Psi12 enters here, and Psi13 enters here. And finally, you have these, now you can produce an asymmetry, but N has also other decay channels which don't contribute to the asymmetry. So for example, from this diagram, you can see that if you cut here, N2 like could decay to N1 phi, and this is something that we don't want. So if you compare the rate of what the things that we want, N2 decay to quarks, with the rate of N2 decay to N1 phi, which we don't want.
Is N1 stable?
N1 is not stable because they all have these quark couplings.
So it decays to quarks.
It decays to quarks.
So in final state you have quarks plus.
Yeah.
And phi is not stable as well. Phi is stable.
Phi is not stable. Yes.
So phi decays into what?
Phi could be stable.
Phi could be
Yes.
stable.
But you can put it at larger than 2 N1 masses, and then it decays. Otherwise, we are stuck with some abundance.
So what's the final state really into the decay? It's quarks plus.
In what?
And
Oh, this one. Okay, this one. N2 will go to N1. N1 will decay to quarks. Phi will go to 2 N1s, and N1s will decay to quarks.
So
This
multiple jets.
yes, and we will explore this at the LEC. This signal.
Will you talk about the Friedel violation later?
Yeah, I'm not talking too much, but I had to like painfully check all of the bounds. Like you could have some meson oscillations, for example, K to K bar, B to B bar. You can also have neutral oscillations. It's true loop in this model.
Because there was interested there are nasty bounds on
Yes,
things.
yes.
Sounds
I had to check. Yes, I also checked the neutron EDM, and that's 3 loops. So you have to like, it only contributes at 3 loops.
okay.
So I didn't do the 3 loop calculation. This is very hard, but I can trust that it's small to parametrically do things, the bounds. But I won't comment too much. I will just mention it. Okay, so if you fix the baryon symmetry to the experimental value, you get some expression. Here is basically this expression for, so I'm choosing the parameter space. So here is the N1 mass, so it's lighter than N2, goes, it is light, it's lighter than 100 GeV in this parameter space. N2 is the y-axis, so I chose like 100 to 200. And then each color curve is a contour for N3, in which some parameters are fixed. So for example, the scale of the effective operator is 2 TeV, the couplings are chosen to be 0.03, and the branch ratio of N2 to quarks is 0.2.
So the couplings are real.
Oh yeah, this should have an absolute, because I'm putting here the sign of the phase.
So the CP violation is the sign of.
Sign of the phase, yes. CP violation is controlled by that. So, and I put a star here just to highlight some benchmark points, which I will comment later on. Okay, so we have this effective operator.
Can you go back?
Yes.
So the typical mass in the benchmark is 30 GeV for N1 and 160
Yes.
GeV for N2.
For N2.
And N3 is heavier.
N3 is heavier. It turns out that if you lower the splitting of N2 and N3, things becomes a little bit easier, but I want to push N2 to be a little bit lighter so that it's more long-lived. But N1 will be very long-lived because it's light, it has more couplings because it's it's a non-normalizable operator. So this effective Lagrangian that I wrote, you can just, it's easier to use some UV completion in which the interactions are all renormalizable. So you don't have like these effective operators. And you can integrate in, if you want, this X, which is a color triplet and has hypercharged 2/3. It will generate that coupling that we want by exchange of X here, 3-level exchange. And this model is kind of interesting because Doesn't allow for proton decay. This is the main thing that it does, because you have some flavor structure in these couplings. JK has to be antisymmetric. So then you don't generate proton decay. If N2, of course, is heavier. If these N's are all heavier than the proton, otherwise they could decay to N2s. You have small neutron oscillations, and this you can estimate, or the baryometer, but this is too low. So the bound is not too strong. You have loop suppressed KK bar and BB bar oscillations. This is what I was talking to Silvan. And this loop suppression will involve all generation of quarks, so you can always choose some coupling to be small and then you get away. And you also have suppressed neutron in the end. So you have to be really careful when you are proposing these models that violate baryon number at low scales. Because of that, you have several different bounds, which are potentially signals one day.
No, no bounds from BDKs or.
Yes, there are bounds from BDKs. So actually, one of the leading bounds is from B to phi K1. No, something. Which is like a Aussie suppressed in the standard model.
B to K, phi, maybe?
A B to K5, something like that. I have to remember. Yeah, because like the standard model is small and then this thing generates, but then you have some bound like on this coupling should be roughly less than 0.1. Then we can produce these ends at the LHC. So you collide two protons, you produce, for example, so we produce one of these ends, N3, and these ends will decay in a chain to these other lighter ends. So N3 can decay to N2, and this scalar can decay to two N1s. Maybe I can draw here. So you collide two protons, you have this X. So here it's two quarks. You have this X. X goes to one of the heavier guy, N3, and one, let me remember. So N3 and one jet. So this is just a quark. N3 would decay to phi, and either N1 or 2. And this phi would decay to N1 and 1. So you have lots of these guys in the final state. They are back to this jet. So we have a monojet signal, and then they will decay displaced at some point. Decay to quarks at some point here. So the LHC is here, and it could decay like this.
You had a slide with C now, but I forgot. But
20 millimeters is the 20 millimeters is the raw. But I'll show you.
What's the
Yeah, it can be much bigger. So here N1 and N2 are produced at LHC through these channels. They will travel long distance and then decay somewhere else. And there are some experiments designed to detect these interactions. So for example, here I'm showing one that is called Methuselah. It's a big facility, like 100 to 200 meters big in the surface of the LHC.
Yeah, it's not millimeters away, right?
This is that's very far. So I'm choosing like a extreme scenario. It could also decay inside of the main detector.
And you have sensitivity to displaced vectors, displaced vertices inside the detector. Right?
Yes, you also have.
HCB, for instance.
Yeah, exactly. So this is a not so good picture. I should have put some scale. Like this box is 200 meters cube, and this is the main detector, the LHC, the Atlas. Well, Atlas or LHCb depends. I just put them near for scale. So this is one that is called Codex V, which is placed nearby LHCb and can detect these displaced vertices at the LHCb. You can also detect them inside LHCb. There is this other one that is called Anubis, which is like this big. It's put in this big tube that is on top of Atlas. It's like they don't exist; they are proposed experiments. But in principle, they can decay displaced vertices.
Codex exists.
No, none of them exist. Only phaser.
Phaser
exists, but you won't be sensitive to this one because phaser is in the direction of the beam axis,
yeah.
and it's like the solid angle is too small to have any events there. But Methuselah is this other one that I was commenting. So here is a plot of the distance of decay and the number of LLPs. So this is like a differential distribution of the numbers. And you can see that and through mostly the case. So ID is inner detector, which is the first detector of the LHC. It will mostly decay inside that. So you can look for displaced vertices inside the inner detector. But N1 can be really long-lived and can probe like from other parts of the LHC detector to these very far experiments that are proposed. And you can see that they have like a significant number of events at high luminosity, which is the next stage after the run tree of the LHC. So you can have 370 events at Matusa, for example, which is interesting. So, yes.
Yeah, you are showing okay, decay length, but you are assuming one benchmark parameter.
Yes.
Does this depend a lot on your parameters?
It depends. It depends on the parameters a little bit.
You have to tune a lot to obtain something interesting.
Yeah. So this is like the one of the best case scenarios. This is why I chose this benchmark point. But if you want to be more broad and see what is like the scope of these experiments, you can look at these other ones. So here we have these couplings, right? The lambdas and lambdas JKs. This control basically the kappa of the effective operator. And I'm plotting here one of them, this lambda prime ds, as a function of these other ones, lambda 3c, oops, and lambda, wait, can I do this? Yes, okay, good. Lambda 3 charm and lambda 3 top. There is a slight issue with the up quark because it has strong bounds from proton-proton to kaon from supercameo candidate, which is something that I never knew before it was possible. So this has to be smaller than the other ones. But these other ones could be large, and they could still generate this. Actually, this one could generate asymmetry. So here are several different bounds. So these dijets is just this model produced the dijets at LHC, so I have a bound for that. This monojet, because as I was saying, this has a monojet channel. You can also have flavor bounds like meson oscillations, B decays. Oh, it's actually B to 5 pi. Maybe there is also K. But if you now do this broader parameter space kind of scan, you have the bounds here for codex B. This is the inner detector of the high luminance LHC. This is Anubis. So it's kind of sad that they are not as good as the inner detector searches because that's going to happen. And then this codex B and Anubis are proposals. But Matuzla is really better than them because it's like a crazy idea to just put this big facility on top of the LHC, so it's very sensitive.
So high lumi makes a big difference with respect to the usual LHC.
Yes. If you were only at the usual LHC, maybe this curve would be around here. You have to go. You have to go a factor of what is 20 in luminosity. So this translates to like.
So high lumi is what, 3 inverse attobars?
Yes, 3 inverse attobars. So it's 20 times the luminosity of the current stage of the LHC. So yeah, that's mostly the idea. Right. So
come on.
so you can spontaneously break as you was anticipating the baryon number, and then you have a number Goldstone boson of baryon number, and then you have to give a name. So we called it Bajaron because there is a majoron. Majoron is the number Goldstone boson of lepton number, so this is like analog. And yes, Gustavo complained about the name, but eventually I convinced him it was a good idea.
Terrible.
Apparently, this is something like in Star Trek, but then
It's Star Trek.
yeah, there's some alien race called the Bajo. I was told. Okay, so you can check that. I won't talk about it. But one idea that we also think is like you can use CP violation from baryon decays, which were measured really recently, like 21 of March this year. And well, you have to do some model building, which we are not finished yet. But like it's not true that the standard model doesn't have a lot of CP violation. You can use like CP violation from.
That has strong phases that
Yes.
gets into the thing, and you cannot separate these strong phases from the CP validation from the top.
That might be an issue.
It's an issue.
Yes. Well, sure.
Talk to Ignacio Vidiaga. You know
Okay.
Ignacio
No, I
Vidiaga?
don't know him, but I
Talk to
would like
Ignacio
to.
Vidiaga. He's expert.
We're still thinking about this, but just maybe announcing this is useful because I can get to know people that know more than I do. Okay, so how much time do I have? Let's see. Okay, it's fine. So let me go to this second part in which I will talk like superficially about electric baryogenesis and some details of the electric phase transition. This is related to this technical paper that it contains like resummation words in the title. But this is, I want to just pass a message that these calculations are really hard and you have uncertainties from everywhere. So it's nice to know what are the places to look for uncertainties, I guess. Okay, so electric baryogenesis, we saw that the baryon number is a really good symmetry of the standard model. We have strong constraints. So maybe it's not a good idea to violate baryon number at low scales if you want to do low temperature baryogenesis. So one alternative strategy is to use the baryon number violation that is already built in the standard model. So that gives you a little bit of room. But then you have to do like more things, not just particle decaying. So here is just a recipe for what you need to do. So the ingredients are, you first need the first order phase transition, because as I said, you need this out of equilibrium phase of the universe in which it wasn't homogeneous, and you can have a hope of generating the symmetry. You also need CP violation, so form these bubble walls, and CP violation would have to happen at the edges of the walls. You need to use the baryon number violation from the standard model, which are related to these phalerons, which do violate baryon number. And you have to avoid washing out the asymmetry inside the bubble, which is the bubble will explain, dominate the universe. And if there is washout, then you are erasing the asymmetry inside the bubble. So these are things to keep in mind. So let me just comment a little bit. So first order phase transitions is this thing in which as you increase temperature, so here's the Higgs potential, if you want. So phi is the Higgs. As you increase temperature, the Higgs potential changes, and it goes from a broken phase, which you have a minimum here at a different place than 0, to an unbroken phase in which the minimum of the Higgs is 0. There, the masses of the particles are 0 because the Higgs mechanism is not operating anymore. And in the middle, you could have something like this thing that has a bump. This is a barrier that separates the 0 minimum.
Is there a simple way just from the shape of the potential? Realize that it's not first order.
From the shape of the Higgs potential.
Yeah.
The Higgs potential is a little bit tricky because you have to calculate thermal potential. And as I will comment, the calculation is not reliable at all. You have to do some resummations. And then you can start to think like, yes, there is a way you need to have a barrier. Then you can look at it.
So the fact that basically continuously shifts,
Yes.
you mean it's not trivial to realize that.
It's not. You can calculate it, but it's hard to trust the calculation because thermal perturbation theory breaks down as I will comment.
So I mean, there's not a simple formula about it.
Yeah, if you look at the 3-level one, maybe you are not guaranteed that you have a first order phase transition. So if you have these two minimas, like you can think of the universe relaxing to different minimas. So you at some point you can form bubbles, which are configurations of the universe that lie around here, and they can expand, or they have some dynamics with the other part of the universe, which is this one that doesn't have a VEV, vacuum expectation level.
So I need to go back. So, but isn't the notation of the bubble a fingerprint of first order distance?
Yes,
Okay.
that's.
Okay. So how can you have bubbles if this transition is second order?
Oh no, I'm not talking about the standard model anymore.
Okay.
So this is like the electric
You want to
barrier.
add ingredient to
You
it.
need that,
Okay.
yes. You need to add something. So if the potential looks like that, you have bubbles. These bubbles expand. So this X position is some place in the universe, which was in the unbroken phase. Then as the bubble expanded, it went to the broken phase. So a lot of particles get masses when it goes. So the second ingredient is CP violation in the bubble walls. So you have this bubble expanding, and you have particles outside. They will bounce on the bubble, and you need to create an asymmetry. So to do that, you have to have CP violation so that you can reflect what you don't want right there, anti-particles. So as the bubble expands, it reflects the anti-particles. It absorbs, if you want, the particles, and then inside you can have more baryons, more particles than anti-particles. So to do that, you have to think about how CP violation works. We're also not very good in cinema. So then you use these phaleron. These are the weird configurations that there are in the cinema model. So we have like these antiparticles here, and once the bubbles go by, before the bubbles go by, you activate this phaleron and you convert this excess of antimatter into other sparks and particles. And then you keep absorbing these sparks. And finally, you need to avoid washing out the symmetry that is contained inside the bubble. So to do that, you need to suppress this phaleron rate inside the bubble. Otherwise, the asymmetry will be gone. So you have to require that the rate of these phalerons should be less than Hubble. So Hubble is with the dynamics of this bubble. And you can do some calculation, and then you end up with a condition that the VAV, so let me go back. The VAV, this value at the critical temperature has to be over the temperature. The critical temperature has to be greater than 1, and these signals are strong first order phase transition. So not only need a first order phase transition, but you need it to be strong enough. This means that the barrier is high enough so that the thing is
Otherwise, this phaleron can also go the other way.
yes. So if these phalerons are a little bit active inside, you wash out the asymmetry rate.
Do you have any effect for cosmology by topological
So
effects or gravitational waves?
gravitational waves, yes, it's here, but topological defects. So these things, you can think of them, these bubbles, they are topological defects, but they expand and dominate. So the universe goes to an homogeneous phase at low temperature. Yes, so not like this. It generally doesn't generate some cosmic series. I guess maybe some weird model would do it. But these bubbles just expand and dominate them. So the time mechanism relies on these first order phase transitions, and if you have first order phase transitions, you have gravitational waves, because these bubbles will expand, and then you have several effects that can generate it. They generally do so in this range of frequency, like 10 to the minus 4 Hz to 1 Hz, or a little bit bigger. So there are lots of proposals actually, so you can look for gravitational waves as a trademark of this electric version. But yeah, so now we have to think like how reliable are these predictions? Phase transitions, they require this complicated dynamics in the universe and the gravitational waves. So I guess we can define these 3 sources of uncertainties. One is microscopic, which I will talk about. It's related to field theory and the calculation of this effective potential and the dynamics of it. It's related to the nucleation temperature when the bubbles start overcoming the Hubble expansion so that they can have a chance to jump in the universe. And this S3 is called the bound section, which is the action of the bubble. But there are other sources of uncertainties. For example, these bubble dynamics are very complicated. They require some of equilibrium and kinetic theory. So you have uncertainties from like what is the velocity of the wall, how much energy they inject, and so on. And also you have some uncertainties from hydrodynamics, like turbulence you induce in the universe or sound wave duration. So you go like from particle physics uncertainties to more cosmological, like and simulational sort of uncertainty. So in this part of field theory, the thing we need to do, the calculation we need to do is calculate the effective potential at finite temperature. There are formalisms to do that. And if you do the one-loop thermal potential, you get something that looks like this, where these J functions are defined as some integrals. So you have this like this plasma, and this plasma interacts with standard model particles. Particles get thermal masses because they are coupled to this plasma. Their masses are modified, so the propagation in the plasma changes. You can calculate what is the effective potential. Doesn't matter too much the form, but you can do it at one. And then you have these masses of the standard model particles. They acquire thermal contribution. So lambda is just some coupling to the particle set. And then you have this thermal contribution. But the problem is that this theory loses perturbativity and at the critical temperature. So quantum field theory, if you want to do some perturbative calculation, you need to ensure that the theory is perturbative, right? So otherwise, your predictions can be very wrong. So one way to see that, we can calculate scary things like true loop contributions in this thermal theory and more loops. And these are called daisies because I guess they look like clouds. And they go as this thing, and this lambda t squared over m squared goes with this power. This n is the number of loops. So when you have higher temperature like lambda t squared is greater than the m squared, this breaks down, right? Because the perturbative expansion is based that this diagonal is less than this one is less than this one. So if they are becoming bigger than the previous ones, then you cannot trace it. So it becomes non-perturbative. And now you have to do something. So one thing to do is to resum these base diagrams. So you put them by hand in the theory, and then you include their effects in the effect.
And how is defined the critical temperature? Is by that relation?
No, yeah, so you spotted a curious thing because usually the critical temperature is around that value, like mass squared over lambda. But this is not, this is like when perturbativity breaks down. It also happens to be where the temperature we care about, because the critical temperature in which the universe is having this phase transition. So perturbativity is breaking down when you have the transition, basically. So that's why at the critical temperature you have this large uncertainty. And you have to be careful because that's where we want to have a good predictive power. So yeah,
So that's this automation, is it like looks like resumming or self energies?
yes,
As well. Series of reverse in the past.
exactly. So you are resumming the self energies which contribute to the thermal masses of the particles. So there's you can calculate like the self energies individually and then put them back into the potential through the thermal mass, which is the basis of these methods, which I want to go into too much detail because it's technical and I don't want to go through the lengthy calculation. But this is one scheme called Arnold-Spinoza scheme. Its philosophy is to include. So this is the one loop which I was talking before. It has like 0 temperature and one loop temperature contributions. But then you include one thing that is called the daisy contributions, which are just this type of diagrams that have these roses. And then to do that, you add like the cubic contributions to the potential and the high temperature. I can talk more about that later, but don't want to go too much into the details. This other one is Parvani. You take the one loop potential, and then since these are self-energies contributions, you just call the mass the thermal mass. So if you instead of putting the 0 temperature mass, you put the final temperature corrections. And the good thing about both of these methods is that it's really easy to implement. You can do it like mathematically fun. But the problem is that it's only reliable in the high temperature limits because the thermal masses are calculated in the high temperature. So when T is much greater than mass scales of your model, and they do not include higher order diagrams consistently. This is something that you have to show. I won't show, but so we come to this partial dressing prescription, which is the thing that we did. This partial dressing it's more complicated. First, you have to solve a gap equation. This gap equation is like something like the Schringer-Dyson contribution that will allow you to calculate the mass, the thermal mass. You pick these thermal masses and you insert them in the first derivative of the potential, and then you integrate. And you have to do that because you want to sum only the propagators and not the vertices. This is a technical thing, but I can talk later. So you have here the propagator. You have a self-energy. You can define what is like a Schringer-Dyson just by saying that the mass of this propagator is 1, this is 0, and this is the 3-level contribution plus the self-energies. But now you're inserting the mass that you calculate inside the self-energy again, and then you have to do it like iteration process as you do the Schringer-Dyson. So the pros is that this is self-consistent at all temperatures if you manage to solve the gap equation, because these self-energies come from the effective potential that you know at all temperature. And they were shown to have a correct higher order loop daisy and super daisy contribution. So they don't have like miscounting problems at higher loops, but they are much harder to implement. So let me quickly go through some case studies. So we just take the 2 Higgs double model that is like the standard one that has a phase or first order phase transition. We include 1 Higgs more than the Higgs that we have. They have other parameters. You can solve the gap equation and find these thermal masses. So here's the full gap equation, and here's what the high temperature approximation used in the other methods give you. And this, you can see they're a little bit different. And you can study the parameter space of this model. So we have, like, for example, this A is a new scalar, and this H is another Higgs that is heavier than the Higgs we know. So these weren't found yet. But this blue is a region in which you have a second order phase transition. And these yellow regions are regions in which you have a first order one. So if you want to do baryogenesis, you want to live here. And this is using partial dressing. So we can compare different schemes. So now I'm looking at the different things of the critical temperature, the nucleation temperature, but they are more or less related. And in partial dressing, you can see you have this thing, and you should still have some first order phase transition. But Arnold-Spinoza gives you a completely different result. Arnold-Spinoza, first off, the phase transition is a different strength. So that's the scale here, the color scale. But also has some weird phenomena which we call electric normal restoration, which will become clear in the next slide. And Parvani is a little bit equal to the partial dress, which is a more reliable method, but it's still a bit off. So not exactly matching this one. If you look at the points that have electric non-restoration in this Arnold-Spinoza scheme, the following thing happens. So this blue in the background here is the zero temperature potential. As you increase temperature, it starts to go up, but then for some reason goes down because of the resummation scheme. So you don't restore electric symmetry at the early universe. And this was the reason we were interested, because we wanted to know if that's true. But apparently it's not true, because you can do both Parvani and partial dressing have a normal behavior of the potential in which you just restore the symmetry as you increase temperature. So finally, let me just comment a little bit. So we have these different schemes, and then you can, for example, estimate the gravitational wave production of that. And here, red is partial dressing, blue is Parvani, 2 different schemes. And you can see that they are really different. So they give like pretty different results. And Arnold-Spinoza isn't even here because there is no transition for this benchmark 0.1. So, but if you go to a point that there is a transition, it's much below. And Arnold-Spinoza currently is the one that's most used. Parvani is also used, but yeah, so they are not so reliable. So my point is that this partial dressing method is superior, like theoretically, to these other ones, but it's much harder to implement. So we had a lot of work to do that. And my main point is like, how much can we trust these predictions? Because everyone uses like this Arnold-Spinoza. And to do that, we need like more refined methods, or maybe automatize this partial dressing thing. And I think there's been a little progress on that, but this is the first application of like partial dressing in a realistic scenario. The other ones were just like toy models of scalar fields, just to see what happens. So I'll leave my summary here because I think I run out of time. But yeah, so like I have this connection of BSM physics to terrestrial searches in the first project, and then this other one that highlights the importance of doing reliable calculations. Thank you. Did I overshoot the time?
You mentioned Arnold-Spinoza, there's no restoration, but you see a phase transition.
No,
There's no phase.
there is no phase transition. This is the weird thing, because you can see that by looking carefully at the potential. So this t equals to 0, it's behind. I put like low opacity just because it would contrast with the higher temperature.
You just get.
Then go up, then go down again. You never restore the
But
symmetry.
then how do you get the gravitational?
No, you don't. You don't.
You don't get.
You don't. In Arnold-Spinoza, you don't get. So, for example, this one, there's no
The
Uh,
benchmark point too, you have,
oh yeah, because there are other benchmarks. Example,
you need some other benchmark you do that.
yes. So I chose like I think like this one for that plot. But if you go to this one, then you have restorative phase transition. But it's off. It's like it's less, it's weaker than the other two methods. General.
Basically, the Arnold Spinoza gives the wrong sign correction.
Yes, yes. So Arnold Spinoza, the Daisy diagrams, they have this negative contribution that gives the wrong sign to the thermal mass, but it's an effect of resummation. It's not like the thermal mass is negative.
Did you try to talk with them or?
Yes, yes. No, them, I don't know if they are alive actually.
Yeah,
They are alive. I didn't talk to them because I'm sorry. Yeah. No, Mariano, yes. If I could, I didn't talk to them, but
Spinoza was a student of Mariano. He also.
oh. Okay. But we talked to like this 2x double model people, they have an industry of generating these phase transitions. And we talked to them, like, but they are German.
Constantine.
Yes. No, Constantine, we didn't talk to him. Talked to Margareta.
Constantine gave a set of lectures in his school.
Yes, I watched them in YouTube. It's very good.
They're very good.
Mhm.
Okay, more questions for Pedro? Yes, Rodrigo.
Yeah, sorry, but I'm not with the energy scale, so maybe these questions.
Yeah,
it's too
sorry.
late, but how about the corrections of gravity here? It's important to do some like room-like effects.
So you mean in the
acceleration is twice higher.
the electric phase transition?
Yes, it's walking efficiency.
I don't know. I've never seen that. Like people including some GI effect. Like of course I have the expression of the universe and that's very
Yes,
important.
yes.
But I don't know about semi-classical effects.
Yeah, like
I wouldn't think so, but I don't know what. I mean, I have to think about it. I don't know. Yeah, I don't know. I don't know if you do.
So I don't see any hands up, so let's thank Pedro again. Break.